Okay, hi. Today I'll be talking about applying probabilistic inference to astronomical spectroscopy. I'm Michael Gully-Santiago. I'm a research fellow at the University of Texas at Austin, Department of Astronomy, and I'm happy to be talking at SciPy2020. Okay, so here's the spectrum of a star, here's the spectrum of the sun, and here's the spectrum of a different star. And the key idea here is that a lot of information is encoded in the spectrum of stars. Astronomical spectroscopy allows you to measure physical properties of stars. So, for example, temperature, surface gravity, atomic and molecular composition are fundamental or intrinsic properties of stars. Extrinsic or kinematic properties include radial velocity, so along the line of sight towards the star, and projected rotational speed on the axis of the star. And other special properties such as mass accretion rate, magnetic fields, dust extinction, star spots, exoplanet atmospheres, the laws of physics themselves can all be measured through spectra of stars. Here are the symbols that astronomers use to denote these quantities, so you'll see these throughout the talk. Some of the best tools for astronomical spectral analysis are built in Python, so that's good for our community. Here are some of those tools in complete lists, and I'll just highlight a few of these for the way of background. So TELFIT is one of these tools for spectroscopy. You can think of it almost as a pre-processing step. There's actually a SciPy2015 talk about it, so I won't dwell too much, but it's here by Kevin Gullickson, a colleague and friend of mine. And the key idea for TELFIT is that it actually removes the spectrum of the Earth. So the Earth absorbs light at specific frequencies according to the composition of the Earth's atmosphere, oxygen and water primarily. And TELFIT predicts where these lines should be, their strengths and positions, and you can then divide by that model and get fairly good performance. So you can find out more information about that. So Wobbly is a relatively new framework that does a similar thing. So it separates the star spectrum from the so-called Earth absorption or telluric spectrum, telluric model. And it does so in a data-driven way, which is that you acquire many spectra of the same star over the period of months or years, and you combine them in a way that takes advantage of the Earth's motion and on its axis and through its orbit that makes the star model and telluric model shift relative to each other. And what you get out is a very high precision composite model and the per epoch precision radial velocities, which are useful for planet finding and other physical applications. It's built in TensorFlow, and you can read about it here. Related to that is SOAP, which is once you've done all the pre-processing steps and you have a target of interest that's actually composed of a star system of, say, 2 stars, you can acquire spectra at different phases, so different epochs, and what you get out is the composite spectrum. You measure the composite spectrum of the 2 stars that are orbiting each other back and forth, and you may not know the templates of those stars. You may not know the spectra of these stars, but you know that they're moving back and forth with respect to each other in a characteristic way. So SOAP allows you to separate out those signals and also gives you the orbit that best fits the templates that would give rise to this pattern of composite spectra. So it's really slick. It's built in SciPy and Python, and you can read more here. It's also publicly available. And lastly, I'll talk about spec match empirical. So this can be thought of as like a nearest neighbor or template matching tool. So you assemble a vast library of precision templates. So these would be very high signal to noise spectra with the same resolution as your targets. And basically you just match spectra that look like the one you're interested in. And it works quite well. It's built in SciPy, AstroPy, Pandas. The one trick here is that it assumes that all stars look like normal stars in your library, and when that's true, it works quite well. So this star looks very much like the spectrum of this star looks very much like this one, especially when convolved with a rotational broadening kernel. But often in astrophysics, new frontiers yield astronomical spectra that look unlike anything we've seen before. So templates, what this means is templates are scarce or non-existent. Ground truth labeling is difficult or impossible. And we have to model our spectra based on astrophysical theory alone. So what we expect the spectra to look like based on our knowledge of physics from the ground and other areas of astrophysics. A Pythonic way to think about this is that we want a Python function that takes in a noisy astronomical spectrum and a tunable theoretical model for how that spectrum could have been generated, and outputs the cloud of physical properties consistent with that data. So that's what this talk is about, and broadly we refer to that process as astronomical spectral inference. It goes by other names, retrievals in the earth science literature. And the key idea is that you have some fixed data and you want to doctor your model to look like that data. You want to tune the model to look like that data. And the set or the volume of models that are compatible with the data produces a probability cloud where you have your best fit, maybe somewhere in the middle, and then you have plausible values surrounding that. And this is basically Bayesian inference here. So why is spectral inference hard? So physics-based models are expensive to compute in general. They involve things like oscillator strengths of all the atoms and molecules present in your photosphere, maybe solving for the scale height of your atmosphere and other physical properties. The models are imperfect. The models possibly have very many parameters. There are degeneracies among those parameters that give rise to similar spectra. The data themselves might have correlated noise, as we've seen from the Earth's atmosphere. And you might just not know the noise properties of your spectrograph or your data perfectly. So drilling down on that first point, which is that the computational cost is high. So due to that computational complexity, what's happened in astrophysics is that self-consistent synthetic spectral models are pre-computed on coarsely sampled grids of physical properties. These are put on the internet for download, and you can download those, and you get a very high precision, high bandwidth model of your spectrum, but only at these pre-assigned grid points. So you can't get a spectrum at an arbitrary value. You just have to see them at these discrete points. So the key question is, how do you turn a coarse grid into a smooth function? And the answer for me, at least, is Starfish, which is a relatively new framework for this type of problem. It's a physics-driven model emulator, sometimes also called like a surrogate modeling approach. It fits all parameters simultaneously, so all stellar parameters like temperature, log G, so surface gravity, metallicity, alpha abundance, whatever. It's sort of agnostic to your model. Whatever the grid points are in the model, it emulates those parameters. It's built in SciPy, Python, scikit-learn, multiprocessing. And here's the key idea. You have data, model, you subtract that, you have your residuals, and you want to minimize the sum of the squares of the residuals, which is called chi-squared. But it does so in a slightly fancier way and alleviates a lot of the problems that have historically plagued spectral inference. So as we saw, and here's how it does so. So with spectral emulation, as I mentioned, Gaussian processes, MCMC and Gibbs sampling, local covariance kernels, and noise scale inference. So it's really a thoughtful and innovative framework, and it makes this much more possible than before. So let's drill down on spectral emulation. So the key idea here is that you want to reconstruct the spectrum in between grid points. And rather than just interpolating on a pixel by pixel basis, Starfish interpolates the weights, the eigenvalues, or the weights of eigenspectra. So it decomposes the spectra on the grid points into a PCA basis, and the weights of those basis functions as a function of the grid points to reconstruct the spectrum tend to be smooth. There's no guarantees, but they tend to be smooth. And you can then fit the uncertainty around those grid points and get an uncertainty in between the grid points of the weights, which then propagates into the uncertainty in your reconstructed model. What that operationally does is yield both the mean constructed model, but also the covariance matrix of each pixel with each other pixel. So like these two lines, for example, may be expected to correlate if they arise from the same physics. And indeed, you see there's higher correlation structure here and here correlating to maybe these two lines. So the net effect, or sort of what this operationally gives you, is that this emulation mitigates piling up at interpolated grid points, and that's been seen in the literature. So here's a reference that where you can see that. But basically, the intuition here is that the spectra computed on the grid points look more like spectra, like physically realistic spectra, than like interpolated spectra. And this downweighting is effectively a way to say, to get the most value out of your physical grid, and be honest about where there's uncertainties from the discretization process. So this is a really powerful part of Starfish. Another powerful part is Gaussian processes, which is increasingly popular in astronomy in general. This is basically saying that you expect some level of correlation structure in your residuals arising from just a sea of slightly off line strengths or model imperfections. And it's an improvement over the conventional chi-squared approach where you assume noise is independent and identically distributed. Here you're assuming that it comes from like a multivariate normal that's the same dimensionality as the number of pixels in your spectrum, and you draw from that. Your data instance is drawn from that. But it also goes so far as to say in special places, the lines might be extra off, and so it builds in these local kernels and inflates the correlation structure in these local places. And that acts to downweight those lines, but still include them in your inference process. So it's a pretty neat approach, and the net effect of this is to avoid overfitting. Basically, with a conventional chi-squared approach, you would overfit. This is subpixel resampling is going to be common to almost any approach of spectral inference, and so there's nothing too new here other than a particularly nice implementation. Uses this intertools chain technique, and you can puzzle over how this works, but you actually assign the low and high resolution samples back into these attributes. It's pretty neat. So it's an efficient way of doing that, and it allows you to get reasonably precise radial velocities. Not extreme, but reasonably precise. Okay, so let's drill down on 3 science cases enabled by Starfish. So primarily starspot, physical properties, the photospheres of embedded protostars, so young stars, and critically evaluating substellar atmospheres. So these are 3 themes I've been involved with over the last 5 years. So first off is starspots. So sunspots are familiar. They've been known since Galileo time, when we first pointed telescopes at the sun safely, and they're seen on stars. So it's hard to see them on stars directly because we can't generally resolve the surfaces of stars except in like this extreme case. But there are sort of abstract ways to get differential measures. So it's relatively hard to count up the total coverage fraction of spots. This is sort of a subtle technique, but with Starfish, we were able to do that. And so in particular, we added 2 new physical parameters, the temperature of the star spot and the coverage fraction of the star spot, in addition to all the normal stellar parameters. And we fit a massive amount of spectral bandwidth enabled by the IGRIN spectrograph at UT Austin, McDonnell Observatory. And what we found is a very high coverage fraction of spots, which might not be a surprise for this particular source just because we happen to think it's among the most spotted stars in the world, in the universe that we know about, a galaxy. But we also were able to constrain, to some extent, it's the temperature or the contrast of those spots, which is relatively difficult to do otherwise. And we find about 80% coverage fraction of spots. So that was one of the most robust measurements of its kind for this application. We also measured physical properties of a very, very young protostar. So among the first stages of the formation of stars, is so early on that really it's hard to measure at all because the star is shrouded by clouds, by dust clouds. And we used 8 hours of Keck time. So the Keck telescope in Hawaii, just to get this spectrum and see these lines that arise from that embedded protostar. And we were able to see that our retrieved temperature and surface gravities are broadly consistent with where protostars should be. And this is tricky in general because the depths of those lines are generally highly degenerate with properties of the disk, and so we revealed those degeneracies. We quantified those degeneracies by adding 4 new parameters to Starfish. So the temperature of the disk, the area, the extinction, and even the power law, the character of the dust. So this worked pretty well, and this is going to inform how we can cope with data from the James Webb Space Telescope. Okay, and lastly is an ongoing project, which is the fundamental properties and physical chemistry of ultracool substars, so basically brown dwarfs. There's a new model grid made by Mark Marley, Caroline Morley, and others called the Sonora Bobcat Synthetic Spectral Model Grid, which goes down to quite cool temperatures, so of order 300 Kelvin, so almost room temperature. Brown dwarfs, which is remarkable. And the key idea here is that we basically take relatively high spectral resolution data on these very cool brown dwarfs, and we're able to measure physical properties and rotation rates down to very low values, and it works quite well. So this is actually some of the first critical tests of these models. At these spectral resolutions. So this is ongoing work with those modelers to quantify how well their models perform and sort of where the models are going wrong, which you can see in these residuals, that there are clearly places where the model might have conspicuous line residuals, which indicates physics that's sort of missing or over or underestimated in some way. So that feedback loop will be dramatically improved by having communication directly from the data back to the theorists in a good feedback loop. Okay, so there's key limitations of Starfish, so I don't want to give the impression that it solves all problems for all data. In particular, there's significant barriers to entry that have led to high interest but low adoption, so technical barriers. For example, tuning the blocked Gibbs sampler is subtle and slow. Training the spectral emulator is another procedure that's really slow. So these are subtle bits to get right. A lot of the physical extensions I talked about are basically just bespoke research code and undocumented forks, and you can find them, but doesn't really explain how to use them for newcomers. There's no auto differentiation, which would be great. There's no GPU support. So these are all things that could be better. So thankfully, Miles Lucas, who's a grad student at the University of Hawaii now, formerly in Iowa, has really done dramatic overhaul of Starfish in general. So it's much more API-like. So rather than very scripty, it's more like an application programming interface. The analysis is made easier by using other libraries. It doesn't assume Gibbs sampling. You can use whatever you want. So it's just much better for probably most applications. And so I encourage you to read the docs and check it out. Here's a demo of how the sort of new API-like approach would look. So you could just say, oh, dust flux is a black body model and with some temperature, and pow, you have some new flux. So then you can go ahead and use whatever framework you want to use for that maximum likelihood or MCMC. So a lot of those problems that we saw are addressed in version 3, so that's great. We're applying for NASA funding to get a lot of this, a lot of the work we've done a little more documented as part of a NASA proposal. But let's drill down on these last two. So auto diff and GPUs. So this would be great if we could get auto diff and GPUs to work with Starfish. Why? Well, GPUs are helpful because the main bottleneck, computational bottleneck in Starfish right now is basically inverting a 1000 by 1000 matrix for the Gaussian processes. You can't use celerite, which is a really fast version of GPs, because our matrices are inherently non-stationary, which is incompatible with celerite. But with a GPU, you could solve exactly this matrix inversion with up to, in my experience on modern GPUs, up to maybe 20,000 by 20,000 matrix. So essentially, almost any arbitrary size spectrum is going to fit into that. So that's great. For autodiff, this is a little more subtle, and if you haven't heard of autodiff, it's almost like magic. You get derivatives of your functions essentially for free. But why it's important here is that there's essentially like a limit to how many parameters you can have in MCMC. So the sort of conventional wisdom is something like 10 plus parameters. You begin to not be able to get mixing of your MCMC chains or other subtle effects coming. But with Hamiltonian Monte Carlo, you overcome that by using exact gradients. So if you can take exact gradients of your likelihood function of your loss function, then you can go up to almost arbitrary number of parameters, or at least many more than what we're used to. And so here's an illustration of that. So here's sort of what you'd expect as the truth. And then here's a particular no U-turn sampler implementation of Hamiltonian Monte Carlo, and it outperforms both Gibbs and conventional Metropolis Hastings. This is also true, this limitation is also true of ensemble methods, so which is popular in astronomy. So MC, which is written by Dan Foreman-Mackey, and implements this algorithm, also is doomed to fail in high dimensions. And so you want to move towards a Hamiltonian Monte Carlo if you can. So enter JAX and NumPyro. So these are both relatively new frameworks, I think in beta maybe, so still very new. And they're great. They offer both forward, so JAX offers both forward and backward mode auto diff, and also CPU, GPU, and TPU support out of the box by using XLA. So this is just awesome. Been really excited about JAX. And NumPyro gives you basically a 100x speed up for Hamiltonian Monte Carlo compared to Pyro, which is the PyTorch version. So this is just like awesome, and I'm really excited about these. And I have some demos online, so you can check these out. This is work with Natasha Batala from the NASA Ames Hack Day, the first one, where we basically just tried to see if this works for toy spectra. And so you have some model that function of temperature, surface gravity, and metallicity, and we just said, hey, can you take the Jacobian of this? Does this just work out of the box? And voila, it just works out of the box. You get exact Jacobians essentially for free or cheap. Which is just astounding to us. I mean, you can even have like if statements and take a Jacobian of that in your function. So to us, that's awesome. One of the really profoundly cool things, in my opinion, is that if you take a Jacobian of a Jacobian of your likelihood function. So this is the Hessian matrix. So this is the second derivative of all pairs of functions. All pairs of parameters of your loss function. You get what's called the Hessian matrix. And if you invert that matrix, then you get the Fisher matrix, which is essentially exactly equal to your chi-squared contours. And so here's a demo of what that looks like. So here's some fake data where we know the answer, which is this red star, and you just do some maximum likelihood estimate to get close to the what we know is the truth. And if you did a grid search over your likelihood function, you'd get sort of this these colors. But if you just take the Hessian and invert that and get your Fisher matrix, you get these contours that approximate that the true sort of posterior true probability cloud. So this is awesome. Really excited about this for applications throughout astrophysics. And we've done now a proof of concept beyond the toy model, which is using NumPyro, JAX, the Hytran, Python API, GPUs to constrain the temperature pressure profile of Earth's atmosphere. So this is similar to like TELFIT sort of approach, but fitting for like 20 plus parameters. And it works. So this is still a very early phase proof of concept, and we're excited about this and moving this towards, for example, brown dwarf models and other things. Okay, so I'll just stop here with the key ideas. So there's excellent Python frameworks out there for spectral inference, including Starfish. Spectral emulation is a great key idea that makes this possible with self-consistent physical models. And I'm really excited about the future promise of JAX and NumPyro, AutoDiff, and GPUs, which will really allow us to ask new questions and push our creativity of what we can do with science at the frontier. So big thank yous to the organizers and Ian Shikala, who's behind a lot of Starfish. That was part of his PhD. Miles Lucas, who's recently overhauled it, and all the people who've been supporting Python and Starfish open source development over the years. So thanks.